Okay. Yeah, I'll let them in. Admit all. Okay, shall we start?
Let me know, then I'll start.
Laura, can we start? Have you all downloaded the thing? Haven't ah? Wait, what? Oh, this thing is covered.
Hmm?
Wait, what?
It's like nothing in the folder.
Huh, really? Then we let them download first.
Yeah. For those people in Zoom, you all can see the slides I share, right? Yeah, just follow them. And yeah, let us know in the chat if you got any question.
Is that what? Nothing is in the thing.
Let me. You should be able to download.
Wait, you all open and then there's nothing inside?
I thought about something. I managed to.
Wait, sorry.
Wait, there are 3 documents in the folder, right? You guys are able to see.
Wait.
I'm supposed to check it. I wrote everything.
Oh, Z4 got nothing. Okay.
Eugene, you can take a screenshot, then take a screenshot of the screen.
Me?
Yeah, then tell the participant to like.
No, I'm sharing the screen. I think they can see, right? Wait, let me stop share first. Wait, what's the issue now? Sorry. Okay. Sorry, give me a minute. Stop share. Hey, what's the issue now? Let me see the file. Yeah, I think can. The zip file got the thing.
Can we start?
Sorry, give me a minute. Let me set the Chrome. Yeah. The screen sharing is paused. Why my screen sharing paused?
Wait, I haven't seen your screen.
Wait, oh, I shared the wrong one. Give me Oh, okay, sorry. Yeah, someone message private message.
It's me.
Oh, it's you. Okay, give me okay. Yeah, for those people in Zoom, you all should see the slides, and yeah, if you got any question later on, we will be going through the lab. And yeah, please follow instruction, the 6 steps to create the folder, which will be used for the practical later. Okay, let's start. Hi, good morning, everyone. Hope you all doing well. Today we'll be going through our topic, which is basic image analysis for machine learning. So, today I'm Eugene, and along with me I have Hui Shen and Pan Pan, who will be presenting today. So about ourselves, I'm Eugene, a year 3 computational biology major student, and for Hui Shen, she's a year 2 data science analytics major, and for Pan Pan, she's a year 3 computer science student. So yeah, So to give you just an overview of what we're planning to do for today's workshop, we'll go through the background and summary of what we intend to do, and about the data set and the software we are planning to use, which will be OpenCV. And we'll be going through exploratory data analysis, where we look at the features of the data set and the examples of the image. Following that, we have a break. And lastly, we have a very important section where we'll be going through the feature engineering. We'll do the filtering, the locate the face, and localizing the facial features. And we look forward to other aspects of the, because this is a few part series workshop, there'll be other workshops that will be connected with our workshop. Yeah, we will explain more about it later on. So to give you a background of what we want to do, have you all done any sorts of work before? Yeah, so you all can understand that employers need to take some sort of attendance, right? But isn't it very troublesome? Where we can ask the employees to do punch card or mark on their own trust system. But could there be a more efficient way or a more reliable way to do so? And I think you heard a lot of potential of ML, AI, all this. And for our workshop, we want to equip the system with ML so that it can identify individual, even if there's a slight change of appearance. So, because I'm not sure whether how familiar you are with ML, let's take a look. Just a quick summary of what ML is. So a simple way to look at ML is that you let the machine learn by itself. And how you do it is you feed the you feed it with data. For our case, it will be the faces, and we let them predict the labels for the new data. We are giving them any information about it. So a side note, so the ML that we are dealing with is the ML we are dealing with specifically is supervised ML. Hence, is where we need the training data as input, where they're assigned to feed to the model and learn more about the data in general. And those training data will be labeled, which will be explained further on. And a side note, for unsupervised ML, the machine is not even given any label, and they just analyze and classify it. But I'm just not going to dive deep. I'm not going to have a deep comparison between supervised and unsupervised machine learning. But just let you all know, we are doing a supervised machine learning for our project. Moreover, it also requires an algorithm. Well, this type of algorithm is different from the usual, where there's a fixed recipe, and it keeps improving. What makes it special is that it keeps improving its accuracy in its prediction or classification through exposure to relevant examples in the training data. So you can imagine the model as a student who want to learn as much as possible from the teacher, i.e. us, in the hopes of taking our role as a classifier. So overall, what's our plan is that we work by comparing the face print to a database of known faces. And if there's a match to our test data with the training data, the system can identify the individual, and that's what we hope for. Okay, let me take a water break first. So all this sounds very easy. So all this sounds very easy, but I'm pretty sure you'll hear this term before used in ML, rubbish in and rubbish out. So to prevent that from happening, we need to do data pre-processing. And that's what we are doing today. Following which, we'll be doing model tuning and model training. And lastly, we'll be doing model deployment to reach our end goal. In this workshop itself, we couldn't, it's not possible to reach the end goal, but we'll be focusing on data pre-processing, which there's a lot to cover. So about the data set that we are planning to use, it's called labeled faces in the wild. There are around 13K images of 5,000 plus people. How we know that is if you look at the website. I don't think we provide the website link, but you can go check it out. Just like this labeled faces in the wild is in Google. If you download a zip file, there are around 5,000 plus people. There are 13K. Let let me repeat myself. There are 5,000 plus name folders with 13K images in total. And for the resolution of each picture, there are 250 times 250 pixels. So these labeled faces in the wall are the public benchmark for face verification. And each folder, each folder is equivalent to one person. And each name folder, you can have one or more pictures in each folder. So in the data set that we've given you, we reduce it by only 5. So just letting you know, there are 5,000 plus people folders to analyze if you're doing the whole data set. So the software we are using along for our data preprocessing is called OpenCV. It's a huge library with more than 2,500 optimized algorithms for computer vision, machine learning, and image processing. And it also has interface for Python, Java, and C++. But for today, for our project, you'll be only using Python. I mean, if you are feeling adventurous enough, you can try the other 2 languages and use OpenCV for that. And for OpenCV, it's fast and easy to code and deploy for CV mainly. So when OpenCV read the image as a NumPy array, because we are dealing with a color image, it will be 8 bits per pixel. And you can use blue, green, red RGB to represent the 256 different combination. So if you remember, red and blue give you purple. Yeah. So all colors can be encoded by the values of the 3 colors and the dimensions of the input image. When you put input image dot shape, the first index will be the height. The second index will be like width, and the third index will be the number of channels. So for our case, we are doing color image. It will be 3 channels. So let's take an example for an image. This is a 4 pixel by 4 pixels image. And if you look at a particular pixel, let's say the first row and the first column, the black pixel, what you will have is blue will give you 0, green is 0, and red is 0, because that's what black pixel represent. And it's done on a 250 times 250 pixels of image. Yeah, just the image itself, one image. So yeah, you are processing a lot of data. So something to take note on later on, soon we will be opening OpenCV. So here's a thing to note: always check the shape of the image array, as I gone through earlier. After you read it, and you can view the image in the notebook itself and compare with the actual image. What I mean by that is that when you run the code in Colab, you can put cv.imshow to view the image, and you can compare with the actual image from the folder itself. You go to a File Explorer and open up and see, are the colorings the same or not? Because you can see later on why there might be situation it might not be the same color. So yeah, let's do some practice now. I'm going to give you all some time to open up the Google Colab. We'll be going through some code. Yeah, just message in the chat if you got any queries, or you can just open on my end. Just let me know. Okay. Yeah, okay, I'm going to go there first. So you all should see this in Google Colab worksheet under the email. We send you an email. So could you open out the email? Yeah. Could you give me some thumbs up? I don't know what. Do I continue? Wei Xuan, you want me to continue? Do you want to wait for them, or we can? I'll just start. Wait, can you hear me? Sorry. Wei Xuan, do I start?
Yeah, I think you can start.
Okay, yeah. Yeah, if you got any yeah, if you just start, just let me know. Yeah, I'm just going to start. Yeah, just thumbs up will do. Thank you. Okay, so this is the worksheet that we have written code for. Firstly, we need to use Google Colab import drive. You run it, and when I run it, yeah, it will say run anyways. Just click that. Take a while sometime. Yeah, so we need to Google Colab. Yep. And yeah, just follow me if you're new to this. Yeah, you mount the drive. It takes a while, so bear with me. Okay, so it's mounted already. So in your Google Drive, this is my drive. I uploaded this image preprocessing workshop, which was the instruction was given earlier on in slide 1. So you put in all the pictures. You have Aaron, partisan, just quick look. Yeah, it'll give you this. So yeah, if you got yeah, you should see this, all the images in, yeah, you see 5 name folders. Okay, everyone can follow. So let's import OpenCV library, and it's pre-installed in Google Colab, so that's great. So let me run this. Yeah, for this code, yeah, I created this code just to if you're lazy and you don't want to unzip it, basically. But just ignore this, I guess. Okay, so we want to visualize our input image. We just take one person, Aaron Eckhart. If you look into here, you'll see one image itself. So we hope to see something similar in the Google Colab. So if you run it here, oh, it won't show your image because this is just reading it as a NumPy array. And how I know is that when I run it, it will give you this image array. So how you see this is quite simple. It looks a lot because there's 250 times 250 times 3. It's a 3-dimension array. And it's ordered by height, width, and color channel as mentioned earlier. So you can see a lot of numbers, but what I would say is the most inner bracket will be the values for blue, green, red value for that one particular pixel in respectively. So for this case, it'll be 0, 0, 0. And yeah, that's for the first row, first column image. So you can imagine that for 250 times 250 pixels. So yeah, I hope that's not complicated to understand. But yeah, and also check the shade because you know it's 250 times 250 resolution, and it's 3. Okay. Yep. Yeah, that's 3 channels. Okay. Oh dear. Why doesn't this work? Well, if you look at the disabled function error, you want to see the image, right? I'll say to compare with the. I was mentioning to compare with this error at heart. You want to compare what other image the same. It's always good to check. But this doesn't allow, this Google Colab is disabled. It's being disabled here. You can run it in Jupyter Notebook. So one other alternative, because you're running in Google Colab, is to use CV2 IMShow. It's the same thing. It's just meant for Colab. Just something for you to take note of when you're you're running OpenCV as a library. So it looks good it's similar to Aaron Eckhart. Yeah. So yeah, we can proceed, and there's nothing wrong with this CV2 IMShow function. So I'm going to go through this part quickly. Yeah. So you want to read all the images because we are not dealing with just one image itself. Whatever I show you is here, we're just running with one image. We want to run all the image, this whole folder itself, this image preprocessing workshop. And when you're running all the image, it's important to understand how your how your directory works for this case. So this is the example. So this is the image preprocessing workshop, that the folder you created, and the next level, you have all the names. You have Evan and Hart, Evan, Gil, so on and so forth. And in each name folder, like I mentioned earlier on, there could be one or there could be much more, many more. We're not sure, but there's at least one of them. So we want to iterate all the name directory, and then we want to read all the image from each directory itself. So we use this function os.list directory to pass in the path and to get all the files in the specific directory. So let's run. Let me just explain the code because it looks quite long, but it's actually quite simple. Don't need to worry so much if you see this code. So basically, you import OS, because you're using this list directory, and the path to directory, this just basically to reach until image preprocessing workshop, the folder itself. And just take note, the read ing is a dictionary where you want to store the key and the value. We'll explain on later on what's the key and what's the value for this case. Okay, so again, let me drink some water. Okay, so we want to go through a for loop because there are a lot of name folder. You can't expect to do one at a time, right? So a good way is to use for loop, os.list directory, path to dirs. What this means is that you will go to image preprocessing workshop folder itself, and you will list down all the name folder. You have Evan, Eckhart, Evan Gill, so on and so forth. And also, we want to filter out .ds store because when we download it, sometimes you have this extra .ds store file, which is useless for processing. So the path to directory, because when you look through it, we can just put it under here to go further inside the image. Because now we are at this level, we want to go to the second level to the name folder itself. So that will be a path to directory. We go further inside. So what's the purpose of it? So that we can go deep into the image itself, which is at the third level here. Okay. So for image in os.list, you list down the particular image. We store it as path to image, where it will be similar to /Evan and Hart /Evan and Hart underscore 0001, something like that. And when you print the path, you can read it. It'll store as a numpy array. And so what I was mentioning, so for the key itself, for the read image key, that will be the path, the image path, and for the value, it will be the numpy array, which I mentioned earlier on, like the 3D array. So if you read it, I don't think it's. I haven't run this yet. Sorry. So you read, and you list down all the path that is being run. So and you read image, and it will give you this big dictionary, which So let's just go to the first one. So so we give you this path to Evan Pina underscore 0001.jpg, and it will give you the array which I mentioned earlier on. And we store as a dictionary, and you know why later on when we're doing further feature engineering to it. So I hope this is not too much. We are going to have a Are we going to have a break now? Which can confirm me? Are we having break?
We have a break after my part.
Oh, okay, after your part. Okay, so now I pass my time to Hui Shen, who will talk more about the feature engineering. I stop share so you can share, or you want me to continue?
Just stop sharing.
Okay, thank you.
Okay, so before we have a break, I think I'll just want to preface some motivation as to why we have to perform feature engineering on the images that we have just read and shown. So, why do we need to identify features in our images for any computer vision application? So, firstly, I just want to start by saying that basically, a computer is just a computer, right? Like basically, what it does is just to provide some automation for like our numerical computations and like something that is more like faster to read our images. But the one thing that our computers don't really have is like the ability to recognize what the image is. So for example, you can take a look at the motorcycle that's on the slides. So basically, can the computer actually recognize that this is a motorcycle on its own? And the answer is no. You will have to actually provide labels saying that, okay, computer, this is a motorcycle. And how can it tell that it's a motorcycle? So this is what you are supposed to actually teach the computer. You're supposed to identify the features for them so that the computer can then recognize that this is a feature that they should look out for whenever they are trying to classify if something is a motorcycle or not. So basically, we can kind of extract like a couple of features from our motorcycle. So for example, like the wheel, or like maybe the engines, or like maybe even the windshield in front of it. So basically, there's a couple of features that you might identify and then pass it to the computer and tell them, okay, these are features that you have to look out for in the motorcycle. And basically what the computer will do is to actually create an algorithm for itself, a set of rules that they will use to extract these features from every single image that they look from then on. So to this feature engineering step, there are a couple of like sub-steps that you will want to take note of. So the first one is actually feature creation. And what this means is that basically you will be identifying like what are the features in the image that the computer is supposed to see, what the machine is supposed to see. And like then you can tell it's like a motorcycle. So basically, this is a manual process where you have to identify like the features, and then you have to tell the computer, okay, this is something that I want to really emphasize in when you are looking through the image. And then the second part is about transforming predictor variables. And you might be wondering what these predictor variables actually means. It refers to the input that we have. So basically, the image that we want to analyze. And what do I mean by transformation? So actually, this will be covered by Pavan later on. So transforming basically involves a couple of processes that help us, not really help us, but help the computer actually identify and like see like certain features of the image better. So a couple of examples include normalization of color, turning our image from a color to a grayscale and so on. And then the third part is feature extraction, and this is where your computer comes in. It's able to automatically transform certain features, like certain images into like basically the feature. So it's able to kind of just split up the image into the features that it wants to see. And then the last part is basically feature selection, and this is the part where you can actually provide weights to certain features. So obviously not all features are going to be as important as others. So for example, let's say I want to recognize like for example a car versus an animal image, for example. So how do I identify if it's a car? So basically you can just compare like by intuition, like a car has more wheels, a car has wheels, while an animal doesn't necessarily have wheels in most cases. So you might think that, okay, this feature might be more important than others, and then you might want to place like a more higher weight on top of it. So basically, important features will have a greater weight, and less important features might either be phased out or have a lower weight. So just a quick explanation of how the computer then tries to classify images. So basically what this does is that what the computer does is kind of similar to, I would say, like printing variations of an image on the same page of the paper. So it's like, how to say, so basically, after you look at one image, the computer looks at one image, it will basically only have like a very blur impression of maybe like how a wheel looks like. So this is our feature, and the computer will take in this feature, but then it might look a bit blur when it only sees one image of this feature. So what you would do after that is basically to feed the computer more images and to actually like have them imprint more on the same like picture, for example. So what this means is that the more wheels it looks at, it will actually the computer will generalize how the feature should look like. So as you can see, at first we only have one image, it looks a bit blur, but after thousands of images, it's actually more clear that, okay, these are like certain features that will help the computer recognize that this is a wheel. And basically what this does is that the computer will be able to generalize on how a wheel should look like. So it will be more encompassing and it will be able to classify certain images better. So basically what I've just explained earlier on is the manual process of performing feature engineering, where you actually have to handcraft like all the features that you want to be included in the algorithm. So basically what we do is like we manually extract these features, and then after that we'll move on to actually passing these images into a learning algorithm. So for example, like a support vector machine or Adaboost, like just some names lah. And basically the algorithm will help the computer recognize if like the image is a car or not. But also in more modern contexts, sometimes basically sometimes a neural network will be used to replace like the manual extracting process and the classification of our images. And a very popular example of this would be like the convolutional neural network, which we also know as a CNN. Yeah, this will be taught in a workshop that's happening after this week. So yeah, you can look forward to that. And basically, now we'll be having a little break before we move on to actually performing our feature engineering.
Okay, so we are taking like 5 minutes break. So meanwhile, right, if you all have yet to download the training data set, you can let any one of us know. Yeah, meanwhile. For people in the chat, if you all have any problem downloading the data set, you all can feel free to text either Eugene or just text in the chat lah, then we'll be able to answer. Yep. Okay. Tell Eugene to share the previous. Okay, so I think we'll resume at like around 9:40. Take the snacks over. Okay, hello. Okay, we'll start with the second section of the workshop. So for this particular section, right, we are later going to go through the code. You can feel free to run the code along with us, lah. And if you have any other question, you can feel free to ask any of us here. For those who are online, you can feel free to text in the chat. Okay, but before we start, right, let me give you a brief overview of what is going to happen. So we are going to go through all these 5 steps to preprocess our image. Okay, so imagine here we have a raw image from our training data set that we have just now. Okay, what we are going to do, first step is we are going to normalize the image. Okay, so that's our first step. The next step is we want to convert the color image that we have normalized to grayscale. All right, after that, we are going to detect the location of the face since we are going to train the facial model for facial recognition system. All right, and then after that, we are going to crop the face portion of the image so that our training data set only contain the information that our model is interested in. All right, and the last step is we are going to locate the important features in our image, such as the nose, the eyes, the mouth, etc., etc. Okay, so first, let me go through the first step, which is normalization. So what is normalization, right? So normalization is basically where we want to change the range of values. Okay, so in this case, it's the pixel value since we are dealing with images. All right, so normalization can actually help us to make sure that each of our input parameters have similar data distribution. Okay, and it also helps to make sure that the range is in the normal range. So what do I mean by normal range? So if you see the example in the slide here, there's this particular image where it's too dark. Okay, and this particular image is a bit too bright. So when we see this based on our human eyes, we can actually say that our images is not in the normal range, right? It's a bit weird. So normalization can actually help make sure that the image, the values in the image is changed so that it's within the normal range, at least to our human eyes. Okay. So that's for normalization. So for now, I'm going to switch back to the code. So you can feel free to scroll to this section called normalization. So to perform normalization in OpenCV, it's actually fairly simple because OpenCV actually have this built-in function that we can use. So this function is called normalize, right, as the name suggests. It actually takes in a few parameters. So the first parameter is actually the source, which is the input image that we want to normalize. The second one is the destination. So the destination is the image that we want to output. So in this case, it's also an array, but we also need to make sure that the size of the array is the same as the source. Okay, the dimension is the same as the source. For alpha and beta, since we are doing normalization, the alpha and beta is the lower bound and the upper bound of the value that we want to normalize to. Okay, and the norm type is the normalization type. So in this case, OpenCV actually provide many normalization type that we can use. So we can actually feel free to click on this link where there will be many normalization type that you can try it out. Okay, so what I'm going to do now is I'm going to first try out normalizing one image first. All right. So as I mentioned previously that I need to specify the destination array, but I don't have it now, so I'm going to initialize it. All right, and as I mentioned, the destination array, the dimension should be the same as the source. So just now in the previous section that Eugene mentioned, right, if you remember correctly, the dimension of the image is 250 by 250 if you were to scroll up a bit. Yeah, you can see that the dimension is 250 by 250. So that's why we are initializing the array as 250 by 250. Okay, so I'll go ahead and run the code. You all can feel free to run along and see what is going to happen. All right. So after we have initialized the array, we can straight away pass in all the parameters to the function. All right. So I pass in the source, the destination that we just created just now, and then the lower and upper bound. In this case, I'll set it to 0 and 255. You can actually try changing the value and see how the image actually change. And then in this case, I'm going to use this normalization type called norm-min-max. So basically, norm-min-max is going to normalize such that the lowest value is going to be 0 and the highest is 255. So as I mentioned, there's many types, right? So you can actually try to change the parameter and see the effect of it. Okay, so I go ahead and run, and then if I were to run this particular line of code, you can actually, like if nothing goes wrong, we can expect that the norm image would already contain the normalized image. Okay, so I'll just run this, and then I'll just use imshow to show the image. So you can see this is actually the normalized version of the image. Okay, but maybe to your eyes, right, it's probably like not much of a difference as compared to the previous image. Yeah, and probably this is because like the this particular image originally it was pretty good already. Yeah, but if you were to look closely at the number, let's say this one is the normalized version, right? You see the number is 157, 129, etc., etc. If you were to compare to the section just now, it's actually slightly different. So like 147, 121, 105. So yeah, so in fact the image is already like normalized. All right, so you remember just now we go through normalization. So what we did is we initialized the output array, the destination, and then after that we apply the normalized function, right? So that's the step. So to iterate through all the image, to apply normalization to all the images, we are going to go through that steps over and over again. So that's why I create another function for this. Okay. So basically what we have to do is to just apply this particular function to all the images so that all the image will be normalized. Okay, and if you remember correctly, just now in Eugene's part, we store the image as a key value pair in this particular dictionary. So this dictionary contains the key, which is the path to the image, and then the value is the array representing the image. All right, so I'll just iterate through the key value pair. For all the value in this particular dictionary, I'm just going to apply normalization. Okay, so this particular block is just applying normalization to all images. Okay, so if nothing goes wrong, after I apply normalization, I'll just iterate through all the normalized images and then show it out. Okay, so you can see it here. Okay. All right, so that's the first part for normalization. So after normalization, we are going to convert our color image to grayscale. So why do we do this, right? When converting image to grayscale, it actually helps to remove distraction from our images. So if you remember, right, the color image actually provide another dimension, which is an extra information. So sometimes we wouldn't want that because it create like unnecessary information, making it harder for the model to learn. So in this case, we want to reduce certain computational requirement so that our model can have an easier time to learn. Okay, so that is converting to grayscale. So okay, let me add. Okay, so yeah, I'm going back to the notebook. All right, so converting to grayscale is also fairly simple because OpenCV actually provide this built-in function that we can just straight away use. Yeah, so for this section, we are going to use this function called convert color. It takes in two parameters, which is the image as well as the code. Okay, so the image, as the name suggests, is just the image that we want to convert to grayscale. And then the code in this case is telling the function that we want to convert color image to grayscale. That's why we are using this particular code, BGR to gray. Okay, we are converting color image to grayscale. Okay, so I'm just trying the steps out first by trying to convert just one image. Okay, so here I will access the key to retrieve one image from our previous dictionary just now. Okay, I'll straight away and run this particular line of code. And then I'll just try to show it just to check that it's correct. Okay, so after this, as I mentioned, we can use convert color to convert color image to grayscale. We pass in the image that we load just now, and then the code BGR to gray. Okay, and I assign to this particular variable. So after I run this particular line, this variable should already contain the grayscale version of the image. Okay, and just to check, you can just use imshow to show the image. Make sure that it's correct, it's already grayscale, no more color. Okay, so to convert to grayscale, we just apply the built-in function convert color. So that is what we are going to do now. We are going to iterate through all the images in this particular dictionary. So similar to the previous section where we normalize, it's the same steps. Okay, for all the value in the read image, so basically for all the images, we are applying this particular function. Okay, that's why we are passing in the value. And then similarly, we pass in the code. Okay, and in this case, I'm just going to store the grayscale image in a new dictionary. Yeah, you can actually feel free to store it in the same dictionary, doesn't really matter. But in this case, just to let us know that this dictionary actually contains the grayscale already. Okay, so after I run this particular line, our dictionary, the read image grayscale, should already contain the grayscale version of the image. All right, so similarly as the previous section, I'll just iterate through all the images, make sure that everything is correct. So if you were to scroll down, if nothing goes wrong, you should see all the images in grayscale version. Okay, so I hope I'm not going too fast. If any question, you can feel free to ask any one of us here. All right, so after converting to grayscale, right, what we are going to do is to detect the location of the face, because we are preprocessing our image for our facial recognition task, right? So we want to detect the location of the face. Okay, and for this, we are going to use something called the pre-trained classifier. The name of this pre-trained classifier is called HAR cascade. Okay, so basically for this one, the HAR cascade is going to help us detect the location. So how does it do this, right? So let me show you how it works. So basically, HAR cascade, once it's a pre-trained classifier, so we can straight away use it. Basically, once we pass in the image, it's going to return all these value, which is X, Y, width, and height. Okay, so maybe you can think about it. If you have all these value, how do we draw this particular rectangle representing the location where the face actually appear? Yeah, you can take a few seconds to think about it. Yeah, so a hint is like you can start with X and Y which is a position, then width and height, then how can you draw this particular rectangle? Okay. So as I mentioned, right, we have x and y, which is returned from the classifier. So let's say this is our starting point. So we have the width and height, right? So imagine like if I were to take this as a width, then this particular point is going to be x plus the width and then y, right? If I were to go up, it's going to be x plus the width and y plus the height. So this is going to be the endpoint of the rectangle, right? So it's x plus the width and y plus the height. So once you have the start point and the end point, you can actually draw this rectangle representing the area where the face appear. Okay. So maybe it sounds a bit like complicated, but actually with OpenCV, we can straight away load the classifier and then straight away use it to return that particular value. Okay, yeah, if you want to know more how the cascade classifier work, you can feel free to read more of the resources here that we have listed out. Okay, but for today, I'll just be loading the classifier and then straight away use it. So this is how you load the classifier in OpenCV. You pass in the data and then you load this particular XML file. So just a brief overview of what this particular XML file is. Basically, this XML file, right, it contains the feature set. Okay, so when we pass this in, the classifier will actually look out for these feature set. So if these feature set actually appear in the image, let's say like here, if the feature set of face actually appear, then the classifier will actually know that, oh, there's a face, right? But let's say if in other image where there's no feature set of the faces, like, yeah, then the classifier will know that, oh, there's not any of these feature sets, so that's why there's no face in this particular image. Yeah, so that's how the classifier know whether there's a face or not. That's why it can detect the location of the face. Okay, so to load the classifier, you can just run this particular line. All right, so to use the classifier that we have loaded just now, so this particular variable is the classifier, we can straight away apply this particular function, detect multi-scale, okay, and then pass in the image that we want to locate the location of the face in this case. All right, and as I mentioned just now, the classifier is going to return the values x, y, width, and height, right? And as you can see, these are the value x, y, width, and height. Okay, but since it returned a 2D array, to obtain the value, I'll just use the index to get the value. Okay, so that's why it's index 0. There's only one element in the array. Okay, and once I have x, y, width, and height, I can draw the rectangle that I showed you all just now. Okay, so to draw the rectangle, once again, OpenCV provide a built-in function called rectangle. Pass in the image that you want to draw the rectangle on. Pass in the start point and the end point. This number one is just the width of the line. Yeah, you can feel free to try to change the value. Okay, so once you run this, you can actually see that the location is being marked, right? As you can see, there's this particular rectangle. So we can see that the classifier actually correctly returned the location. Okay. So why do we want to locate the location of the face, right? the thing is we are pre-processing the image for our facial recognition system. So our model actually care about the face, right? Not other part of the image. Okay. So after locating the location, we are just going to crop the image such that it only contains the face portion, which is the information that our model actually cares about. Okay, so if you were to see in this particular image, this is more of the extreme example where you can see there's like the face, okay, but there's also other objects, other information that our model don't care about. So that's why we want to crop only the face portion and eliminate all other information. All right. Okay, so let's see how we can actually crop the image. You can once again like try to think about it. How are you going to crop the image given this particular rectangle? So the easiest way, right, is to just crop based on this particular rectangle, right? And we are done. But then if you see this particular rectangle, if you were to crop this, right, certain important features are missing, like the chin, the ears, maybe part of the ears, and the upper part of the head. Okay, so we also don't want that. The ideal case is if, let's say I have a padding called P, what we want to crop is this particular red rectangle, okay, where P is actually the padding. The gap here is the padding P. You see, there's all like P here, the padding. Okay, so the red rectangle is something that we want to crop. Okay, and as I mentioned previously that an image is simply just an array, right? Which also means that we just want to include the part of the image from here to here and from here to here, which means we only want to include all these rows and then all these columns within the red rectangle. Okay, that's why our crop image is just a restricted original image. Like we are restricted the row and column of the original image. Okay. All right. So similar to the previous step just now, we have this particular starting point, the X and Y. All right. So you can think about what are the coordinates representing this particular red rectangle. There should be like 4 values that you need to change to restrict the row and column. So you need to restrict the row from here to here and the column from here to here. So what should be the value? Yeah, you can try to think about that. Okay, so let's start with the row first. As I mentioned here, right, is a padding. So if we were to restrict the row first, the row should be from here, right, which is just y minus the p, because we are going down. Okay, now let's go up. So what should be this position? It's going to be y plus the height plus the padding, right? So that's why it's going to be y plus the height plus the padding. Okay, so that's the row. Now we can think about the column. Okay, so let's start from this point. So what is it going to be? So when we minus the padding, it's going to be x minus p. All right, and then it's the same y because the same height. After that, let's go to the right. So it's going to be y plus the width plus, sorry, x plus the width and then plus the padding. Okay. Yeah, so the row is going to be this particular value. Column is going to be this particular value. Okay, and then we just pass into to restricted the row and column. Okay, so it's simply just like array slicing, just that in this case it's like 2D array. Okay, so let's try to do all these steps in our notebook. Let's try to code it out. Okay, so as I mentioned, right, cropping the image is just array slicing, but in this case, it's a 2D array. So that's why we pass in these particular value to slice the row as well as the column. Okay, the padding for this one I set to 50 just so that it's clearer that it's being cropped. You can feel free to change the value and see what is going to happen. So if you change to upper value, then the image is going to be a bit larger compared to a smaller value. Okay, so if you run this, you can actually see that the image is being cropped, right? Certain parts has already been cropped, okay, compared to the previous part. Yeah, maybe this one is a bit like not too obvious because the padding is a lot. If you reduce the padding, then you can see a more obvious version of the crop image. All right, so the steps required to crop the image is just we use the classifier to get the location. Once we have the location, we can use all these locations to do array slicing. Okay, so that's the steps. I'm just going to create the function representing all these steps. All right, and I'm just going to iterate through all the images in the dictionary to apply the function so that all the images will be cropped. Yeah, in this case, I set the padding to 60. So how do you know that like 60 is the ideal value? So in this case, like we actually tried out and we thought that like 60 is the value where it actually help in the next part. But when you actually do the project, you need to try out different values, see which one works best. Okay, it's not like we magically appear with like this particular value. Okay, so once I apply the crop, once I run this particular line of code, all my images should have already been cropped. Okay, so just to mention, right, in this case, I'm just storing the key value pair similar to all the previous section, just that in this case, I'll just store it as the file name and the array representing the images. So that's why I do some slicing to obtain the file name. Okay, this one is just taking the last two value. Okay, and if you were to show the images, all these are actually the cropped version of the images. Yeah, so as I mentioned, in this case, it's not that obvious because we provide a lot of padding. Yeah, and actually the reason why we provide a lot of padding is because if you were to observe all the images in our training data set, right, the face is actually already quite clear in the image, like the image only contains more or less the face. That's why we provide a lot of padding. So yeah, that's the reason behind that. Okay. So I think that's it for my part. So I'll pass my time back to Huishen to go back to talk more about like localizing the important features like the eyes, nose, mouth, and why we are going to do this.
Okay, so basically, now we'll be going through how to localize our facial landmarks. So firstly, what do you guys think it means by localizing facial landmarks? I give you some time to think about it, but essentially, we can split it up into localizing and facial landmarks. So what does facial landmarks actually mean? So basically, we'll be looking at details that we were previously unable to crop, like previously unable to see just by cropping the face alone. So for example, just now Pan has really surfaced on how to actually crop the image, but we have yet to actually look into like the intricate details of our face. So for example, like the eyes, the nose, the mouth, the chin, etc. So these kind of things are like the things that actually set people apart from one another, in the sense that, like, oh, you have a sharper nose, or maybe you have like a wider chin, for example. So a lot of these details can only be identified if we identify these facial landmarks. Yeah, so basically I'll just be calling like the eyes, nose, the mouth, facial landmarks for this workshop. And basically what we'll be doing is to localize them. And localization basically means identifying the borders of these facial landmarks. So basically I'll be trying to locate coordinates on the face where, oh, okay, maybe the eyes are enclosed inside it, the eyebrows are enclosed inside it. So this is what I mean by localization. And you might ask, like, what are the applications of this process? So basically, sometimes we'll be using it to identify like how, like if we're smiling or if we're frowning, other things like biometrics. So like identifying who you are just by looking at the iris, for example. And yeah, so basically we'll be locating these points of the faces that we have in our data set. And yeah. So in order to do this, actually we are pretty lucky that OpenCV does have a application programming interface, also known as API for short, that actually does this. And the name of this API is called FaceMark. So basically, what FaceMark does is that it is the name of like an interface that allows us to, in our code, identify certain facial landmarks. And there are different implementations of this API, which I've already named for you guys below. So the first one is actually Kazemi. It's basically an ensemble model of decision trees. The second one is AAM, which is an active appearance model. And the third one that we'll be going through today is the FaceMark LBF, which stands for local binary features. So one of the reasons why we are going through LBF is mostly because the Python implementation is actually available online. And the rest, if you're feeling adventurous, you can kind of like study how these models actually work and try to implement them yourself. Or you can, alternatively, you can try to actually use these models in other programming languages, such as the C++ and Java that we have already mentioned earlier. So now I'll just go through how local binary features actually works. So the most important thing you need to take note here is that local binary features, as the name suffices, uses a binary system. So basically, what do I mean by this? So we'll start off with like the diagram in the lower left-hand corner. So what's happening here is that each pixel in the image each pixel in the image will be converted into a grayscale and given a grayscale value. So let's say we have 9 pixels over here, and we have converted them into grayscale. And we'll look at one specific pixel, which is the center pixel. So in this case, the center pixel has a grayscale value of 4. And now what I will do is that I will basically compare the grayscale value for this center pixel to neighboring pixels. So if you just try to understand how the binary mapping works here, basically, if I compare the center pixel to, say, the top right-hand corner pixel, so it has two different, so basically the center has a grayscale value of 4 and the top right-hand corner has a grayscale value of 1. So any guesses as to what then will I map it as? So basically, if the center pixel is has a grayscale value greater than the neighboring pixel, the neighboring pixel will be mapped as a 1 in the binary mapping. So zeros and ones. And let's say if I compare to the bottom, the pixel below the center one, between 4 and 7, which one is greater? Bottom one, right? So basically, what happens is that the bottom pixel will actually be mapped as a 0. And basically, what I'll do is that I'll do this for all the 8 neighboring pixels. Or if, in the case you're dealing with like a corner pixel, so there will only be 3, for example. And so after that, what happens is that I will actually map each neighboring pixel starting from the top right-hand corner with a exponent. So basically what this means is that the top right-hand corner pixel is going to be mapped as 1 times 2 to the power of 0. And this will basically happen like in a clockwise fashion. So 0, 1, 2, 3, 4, and so on until we loop back. So the second pixel over here will take 1 times 2 to the power of 1. And so for example, a negative example, 2 to the power of 3 times 0 is just 0, because like 0 multiplied by whatever is 0, right? And what we'll do is then we will sum up this binary, like basically these 1s and 0s multiplied by their 2 to the power of their exponents, and you will get a certain value. So this value will then be useful because later on we'll basically be mapping these values onto a basically we'll be visualizing these values. So take a look at this image here. So basically this is our original grayscale image, and after we have run it through the local binary features algorithm, basically this is what you get. Yeah, so it looks a little bit funny, but essentially what you can notice is that some of the features are like some of the features of the face are very obviously mapped in the LBP version. So for example, like the eyes, like the eye bands are very obvious from the contrast of the black and white in the LBP image. And for example, like the lips are also very obvious based on just, the black and the white contrast between some of the lighter regions and some of the darker regions in the original image. So what this means is that the local binary features algorithm actually identifies facial landmarks by contrast in lighting and contrast in color. So then what the model does is that it actually compares like the pixels of the images by contrast, and then identifies certain pixels, 68 to be precise, that will be likely to enclose our facial landmarks. So now to actually surface what I mean, we'll be moving on to the coding part. Yeah, okay. Okay. So remember what I said about the model being available online. So the thing is that because there is no like local implementation available on OpenCV for Python, we will actually have to download a configuration file for this FaceMark LBF model. So what we'll be doing is we'll be using this library called the URL library and a specific subpackage called request. So basically what this does is that it sends a request later it will send a request to the repository that actually contains our configuration file. So I'll just be running this to import the package. And over here, we will then, so basically the link is really available for you guys. So you can actually take a look, but essentially we will just be using this configuration file, which is the .yml file. And so now we will have to save the string representation of this link in a variable called LBF model URL. And we will specify the name of the configuration file as LBF model. And now what we'll be doing is just essentially download the file. So yeah, in our case, actually the YML file is already downloaded. So if I were to run this, I would get file exist because it already is available in our directory. But in the case that you're running this for the first time, that you're running this snippet for the first time, you should get a file downloaded. And basically what happens is that we will use this function called URL retrieve to actually download this model, this configuration file from the link. Yeah. So the documentation for this should be available online. And so at this point, you should be able to see the LBF model.yml available in your drive. And so now we can actually move on to using the model. And as before, with the HAR cascade model, it's quite similar. So basically, we will have to actually instantiate, like create an instance of the model that we want to use, which is the FaceMark LBF. The method is really available. So all we have to do is just assign this instance to variable called FaceMark. And from there, as we have really mentioned earlier on, the model is not really available in this instance yet. So what we have to do is to actually load the model, which is our configuration file, into this instance, which is FaceMark. And what we want to do here is then, like similar to the HAR cascade case, we will have to iterate through each of the keys, each of the values, which I have named as path and image, just to be precise, explicit. In the crop images dictionary, we will feed every single image to see if like they can identify the facial landmarks, as well as return an array of the coordinates of each of the 68 landmarks. So we'll just run this. And yeah, so in order to show what I mean regarding the array, I'll just run this as well. So it might look like a lot of things, which it might be, but it is also pretty simple to understand in a sense. So the round bracket outside basically just means that it's, oh, hold on. Yep, it's actually available in like a tuple. And basically our array is the 0th element of this tuple. And then within this, you can actually see, okay, there's the 0 element is this NumPy array, right? So now we want to look at what's inside this NumPy array, which is the first set of brackets, the outer set of square brackets. And this is basically like the set of coordinates we have as landmarks. And within the inner bracket is basically a list with our X and Y coordinates that we will be plotting later on. So yeah. And the data type for each of these coordinates is actually in a float. So this is something that we have to actually keep in view when we plot the facial landmarks on our face later on. So, but for now, we will just be running through and just confirming that, okay, we have 68 sets of coordinates. And each of these coordinates has an x and a y coordinate, which is why there are two values in each of the lists. So now it should be quite obvious that the LBF model does return 68 facial landmarks in the form of x and y coordinates. So now we'll be moving on to actually plotting these landmarks on the image. So we'll be doing a before and after comparison. So what happens here is that I will use image show to actually show our previous image. So this is before the landmarks are plotted. And as I've already surfaced, I want to refer to the zero element of the tuple. So I will refer the zero element as a landmark. And then within this array, we have a couple of we have 68 sets of coordinates. So I will refer to them as a coordinate set. And within each of the coordinate sets, we have x and y coordinates, which I will also be calling them coordinates without the s. And then what happens here is that we will then be referencing the zero element of the coordinate set as the zero element. So the x coordinate refers to the zero element, and the y coordinate refers to the first element. So if you're not sure, you can just kind of like refer to the landmark variable that we have already set for ourselves earlier on. And now we will be plotting it using OpenCV.circle. So it's something like drawing the rectangle, but we're drawing a circle instead on the face. Not really on the face, but on the image with the face. So yeah, you can actually specify a couple of other parameters, including the thickness of the circle, which is 1 in this case, the color, which is white. Basically, all of the values of RGB set as 255 means that your color will be white. And if it's all zeros, then it will be black. For the rest, you can kind of experiment yourself. Feel free to change the values and try it out for yourself. And 1 refers to the radius. So then all you have to do is, after I've drawn, then I just kind of want to see how the image looks like. In which case, if done correctly, basically you should be able to identify certain landmarks on the face. So for example, like the chin, some parts of the eyebrows, the eyes, the nose bridge, and and some parts of the mouth. So now what we want to do is just do the same with multiple images by implementing a dictionary to store all of these landmarks. So below this is kind of a pretty long set of code, but I will kind of run through one by one, line by line, just to make sure everyone's on the same page. Before that, we just need to make sure that we'll be able to actually find these images in our local repository, local directory later on. So what I need to do is to actually use a function called image save cv.imsave to actually save these images into our directory. And later we'll be doing so in, so I'll just open up the drive. Give me a moment. Yeah, so basically later on we'll be saving a folder inside this image preprocessing workshop called image preprocessing workshop -landmarks. So that's the folder that we'll be creating to store all of these images with landmarks inside later on. And the reason why we actually have to create the folders first is because cv.image_save, right, actually doesn't it doesn't like auto create the directory for you. And in fact, when you try to save the image in a directory that doesn't exist, it will not throw you an error. So that's what I mean by fail silently. And in order to, so basically what we have to do is to actually, once we have the images with landmarks, we will have to create each of the folders that will include the images with landmarks. So let's just get right into it. So firstly, I'll be making use of some handy packages that you might come across sometimes, even in other contexts, such as the regex package and the OS package. So we'll be using this to help us create a subfolder within the image preprocessing folder, which is the landmarks folder. So we'll be importing the regex package. And then we'll initialize the dictionary that's called landmark image. And for the convenience of this workshop, I've already kind of like explicitly shown on the design, which is basically a dictionary of paths and a tuple of images and landmarks. And from here, all you have to do is to actually, like before, check that the facial landmarks can be detected, and get a set of landmarks for each of the faces by fitting an image into the face mark model. And then from there, I will just save the path as a key to landmark images, and the value will basically be the original NumPy array with a set of landmarks. So basically the 0 element inside landmarks and the coordinate set. So from here, you might notice that, okay, the path, right, is actually, if you try to print like path within the loop itself, you will notice that this is basically, it returns you like the name underscore like the number of the number label for the image, so 0001, and then the file format, which is .jpg. So let's say if you want to create a subfolder, would you include the .jpg inside? Like normally no, right? You just create a name with, like create a subfolder with just the name only. So something like this, instead of .0001.jpg, we just want the name as our subfolder. So what we will be doing is just use a method available in the regex package to actually remove this. For the sake of this workshop, I'll be just going through this really fast, but basically this kind of tries to match to our path if you can identify a pattern which is underscore digits, as many digits, .jpg. So basically what it does is that it identifies in the path this specific component, underscore 0001.jpg, and then it replaces it with an empty string, which is basically nothing. So what you should get as person path in the end is just Aaron Grill in this case. So now with this out of the way, we can actually kind of keep this in view. We'll use this later on in the latter half of the code. For now, after we have fit in the model, we basically just want to refer to the value as a pair again. The value in our landmark images dictionary. So then we will refer to the image within this pair as the 0 element, and the first element of this pair is the landmark. So our landmark coordinates. And basically what we'll be doing here is just kind of like before, we will in the code above kind of draw these coordinates onto our image. So far it's kind of like what we have already done previously. So now we want to actually save these images. Let's say if it works correctly, we want to save these images with landmarks into the subfolder called with extra landmarks on it. So what this does is I will need to first import the path package, sub-package in the OS package. And basically what this does is to help us identify if the path exists. So in this case, we want to create the subfolder for landmarks first in order to create like other folders within it. So we just want to check if this path exists in our directory, which it doesn't at the moment. So if it's equal to false, it will actually make the directory for us. So basically what this does is that it creates this folder within this directory. And after that, we want to then create a subfolder for each of these people. So then we initialize a new variable, path to save image with the folder path plus the person's name, which we made use of regex to actually obtain the string for. And then similarly, if the path doesn't exist, we'll make the directory. If it exists already, then basically what it does is just to rewrite the image. And finally, we get to the bottom, which is basically the point where we write the final image, not as a NumPy array, but actual JPG into basically the subfolder for that person. And then save as a file, which is the person path, basically the name underscore landmarks.jpg. Yeah. So yeah, this is a very long set of code, but if run correctly, you should get basically these images and they should be saved soon to the folder itself, but we'll have to wait for a while because saving actually does take quite a bit of time. So yeah, you should be able to see this subfolder called with extra landmarks at the back. And if you were to open this folder, you should get basically the subfolders with all your names inside, the names of all the people. And then if you look at Aaron Eckhart, our favorite guy, so you should see that the landmarks have been successfully plotted onto his face. And yeah, so that is how you localize face marks with a publicly available model, sorry. So yeah, that is all for this data pre-processing workshop, this image analysis workshop. So in the future, the workshops team will also be organizing 2 more workshops to this CV project, which is the model tuning and training workshop, as well as the model deployment workshop, which will be available in future weeks. So if you're interested, do keep a lookout for those as well. And if not, that is the end of the workshops. If you have any other questions for us, or if your code is somehow not working, or if there's anything you're curious about, you can feel free to ask us. But if not, that's the end of the workshop. Thank you for your time in this workshop. Yes.
Hello. Okay, for the people online, for the people online, right? If you all have any question, you can stay back. Otherwise, that's the end of the workshop. Okay. You can either ask here or in the chat. Either is fine. Yeah, any question can feel free to ask.
Okay, answered. The time complexity is O(n)(n) because O(n)(n), which are the dimensions of the image for this landmark detection, because we need to check every pixel and enable the pixel. Exactly. You could definitely try out those. You could definitely try out like whether or not you do larger than or lesser than. I think that overall you should be getting the same edges basically. Because larger than means that you're just like having the edge this way, right? Lesser than means that your edge is only this way, that's it. Okay. You need to take one last picture of all the organizers, so then you need to switch on his camera. Thanks.
Yep, his image his video is on now.
Everything going okay?